Good morning, Calc fans. How we doing this fine Monday morning? Welcome back from spring break. I hope everything has gone well during spring break. You got able to relax a little bit, spend a little bit of time with your family. I think we've all been able to spend a lot of time with our family. I hope you're feeling well. I hope everything is going well in your household. I hope everybody's staying illness free. It's sort of nice, it's sort of warm outside right now, but it is raining pretty good. Promises are it's going to get a little bit colder before it gets warmer again. So we just have to bear through this week. The grass is going to be growing quite a bit, so if you have some timing, maybe go out and mow the yard. But once again, I hope everything's going well for you. I hope you had a good spring break. We have to continue to forge through. We have one more chapter to go through in calculus. The idea of integrals. We've talked about some indefinite integrals. Now we're going to go through some definite integrals. And what is the meaning of an integral? So that's what we'll be dealing with today. Once again, if you have any questions, feel free to comment me, and I will respond back to your comments through Google Classroom. Still trying to figure out Google Meet, so I know I'm supposed to have office hours from 12 to 1. If you want to ask questions through comments, that's fine. I'll answer them back at that point until I can figure out how to deal with the Google Meet. Still working on that. So today what we're going to deal with is we're going to talk about the idea of integrals. Once again, we have one chapter left to go. This will take us to probably about the first week of May, second week through the second week of May. Somewhere right around that range, and then we'll start prepping for a final. Hopefully, I miss you guys. Hopefully we're back into a normal setting, in the classroom setting at that point. We'll keep our fingers crossed. Still continue to do your social distancing. Make sure we do our part in regards to trying to get us back to some sort of normalcy, because I would like to be able to get back and be around you guys and talk with you guys again and be in a classroom with you guys again. So hopefully we can get back to some sort of normalcy here. Today we're going to start chapter 5. Once again, this is the last chapter we'll deal with, and we're going to talk about the idea of an integral. When we were finishing up chapter 4, we had the integral, which was an antiderivative. When we talked about the antiderivative, that undid the idea of a derivative. But we also called that an indefinite integral. Today we're going to start talking about a definite integral and the application of what an integral will do for us if we put some numbers to this, outside of just being able to undo the idea of a derivative. So we're going to talk about the integral. When we talk about an integral, it is the area between the x-axis and the graph of a function. The area between the x-axis and the graph of a function. And once again, if I'm going too fast, hit your pause button, and then whenever you catch up, you can hit the go button again. The area between the x-axis and the graph of the function, once again, I'll promise I won't continue to talk when the pause is going. Your opportunity to shut me up. We have what is called a subinterval. These are smaller divisions of the interval. Okay, so we talk about the area of the area between the x-axis and the graph of a function. And we could say over an interval with this, and x is a member of A to B. So if we take a look at a specific domain from A to B, that is an interval that we're going to calculate the area of. Okay? We're going to calculate the area between the x-axis and the graph of a function over an interval from x equal to A to B. And subintervals are smaller divisions of the interval. So we break up the interval from A to B into smaller divisions. What our first part that we're going to be dealing with here is we're going to look at approximations, how we can approximate this amount of area. So we have subintervals, the smaller divisions of the interval. We have partitions, and these partitions are values from the domain that are the endpoints of the subinterval. So our partition values, and they script a P with this, is we take our interval from A to B and break it into smaller sub-intervals, and the endpoints of those small intervals on our domain here are the partition values. And we'll look at this here in a second. Okay, so values from the domain are the endpoints of the subinterval. We're going to take a look at the function f of x equals x squared plus 1. We're going to look at an interval from x is -3 to 1, or -1 to 3. So this is our interval that we're dealing with here, from A to B. And we're going to do a delta x of 1. That just tells us how big our subintervals are going to be. So if we take a look at our partitions, okay, our partition values and our subintervals, what this will be in regards to our subintervals is if I take a look at the subintervals, I'm going to go from -1 to 0. Because my delta x is going to be 1, that's going to be how big my spaces are. Then we have 0 to 1, 1 to 2, and 2 to 3. So these are our subintervals. Because my delta x is equal to 1, I'm just going to count up on my number line. If I have a number line here, I just go from I'm going from -1, 0, 1, 2, and 3. That's my interval I'm dealing with here. So my subintervals, my spacing, my subintervals is just going to be a value of 1. That's my delta x here. -1, 0, 0, 1, 1, 2, 2, 3. My partition values are the endpoints of these subintervals. Now we don't want to repeat the values over again. So we're going to put this in a set notation. So I got my braces there. We have -1, 0, 1, 2, and 3. These are the partition values. So my subintervals, I break them down with my delta x equals to 1. And my endpoints of these subintervals, I don't repeat them, are just -1, 0, 1, 2, and 3. Those are the partition values. Now when we talk about a Riemann sum, a Riemann sum is the sum of the areas of the subintervals. The sum of the areas of the subintervals. That is called a Riemann sum. And we're going to be looking at some approximations of these areas, the addition of all these areas of the subintervals. We have a total of 6 different approximations that we will deal with. We have an upper sum, we have a lower sum, we have a midpoint sum, we have a trapezoid sum, we have a left sum, we have a right sum. So we have 6 of them that we will go through. We're just going to be dealing with 2 today, and that's called the upper and lower sum. We'll spend 2 days on this. Okay, the upper sum, no, I'm sorry, is the Riemann sum of the rectangles created by the partition lines. So we have key words here. We have rectangles that are created by the partition lines. Here's our partition values. The x-axis and the horizontal line drawn intersecting the graph at one point that is entirely above the graph of the function. Okay, so we have the Riemann sum of the rectangles created by the partition lines, the x-axis, the horizontal line drawn intersecting, I guess that should be intersecting, the graph at one point entirely above the graph of the function. That's key. The idea of an upper sum, we have to say above the graph of the function. Now, this is confusing to begin with. Okay, it's a lot of verbiage to try to describe what's going on here, but we'll go through some step-by-steps what we have to do. Okay, we're looking at the function. of x squared plus 1. Okay, we have partition lines. Once again, our partitions are -1, 0, 1, 2, and 3. So we draw vertical lines in each of the partition values extending above the graph of the function. What I suggest you get out is a straight edge here and work through this. So we're going to draw vertical lines at our partition lines. Okay, we draw vertical lines in each of the partition lines extending above the graph of the function. So that's what we did. -1, 0, 1, 2, and 3. We draw a horizontal line intersecting the graph at only one point and having the line stay entirely above the graph of the function. Now here's my function f of x equals x squared. I want to draw a horizontal line that intersects the graph of the function at one point, and this line must stay entirely above the graph of the function over this subinterval. Okay, so we're going to stay above the graph of this function. So here's the graph of my function right here. I want to stay above that, entirely above that, and intersect this graph at exactly one point. And this line has to be horizontal. So I'm going to draw it there. So what I've now formed here is I've formed a rectangle. Now mind you what we are trying to approximate. Okay? Going back to our definition, the integral is the area between the x-axis and the graph of the function. So what we are looking to estimate here is we are looking to estimate this amount of area. So this is what we are trying to estimate right here. And what we eventually do is we'll eventually calculate it, exact value, but for right now we're just going to estimate it. So what we're looking to estimate is we're looking to estimate this amount of area. And the upper sum is one technique of estimating this entire area. And once again, we're looking at the subinterval from the interval from -1 to 3. We're looking at this interval. We want to calculate this area. So we're going to utilize the idea of approximations, and the upper sum is the one approximation. Where if what I've just drawn here is I've just drawn a rectangle. Now you can see that this rectangle here is not going to be exact to this amount of area right here. But that's okay. We just want to be able to approximate at this point. Well, if we look at the subinterval from -1 to 0, we want to calculate this area. Well, how do we calculate the area of a rectangle? It is base times height. So we're looking at our base times our height. Well, if we look at our base, here's our base. Our base is a value of 1. So we have a value of 1 here as our base. The question is, what is the height of this graph? Or what is the height of this rectangle? Well, that's where the idea of intersecting this graph is going to help us out, because our height here's our height. It goes from the x-axis to this point right here. Well, the question is how do I find the value of this height? Well, this is also the function value at -1. The function value at -1 is my height of my function. So we have our function value at -1. Our function value at -1 is -1 squared, which is 1, plus 1, which is 2. So we have 1 times 2. So the area of this square, or rectangle, is 2 squares. If we look at the subinterval from 0 to 1, now we're going from 0 to the value of 1. Here's our partition lines. Here's our x-axis here. We have to draw a horizontal line that intersects the graph of the function. So here's my graph of my function. At exactly 1 point, okay, and stay entirely above the graph of the function. And it should look very similar. Drawing from this point over to here, I have the exact same value. So my area here, my base is still a value of 1, but my function value, my height is this function value right now. So we have our function value at 1. So we have 1 squared plus 1, which is 2. So we have 2 squares. If we look at our subinterval from 1 to 2, I have my x-axis here. I need to draw my horizontal line. So my graph, I intersect my graph at exactly 1 point. So here's my graph. So I'm going to draw my horizontal line in, and my horizontal line has to stay entirely above the graph of this function. So I draw my rectangle, or draw my horizontal line here to complete my rectangle. My base is still 1, but the height of this rectangle is now this point right here, which is our function value at 2. So we have our area is 1 times our function value 2, where our function value 2 is 2 times 2, which is 4 plus 1. So we have 1 times 5, which is 5 squares. And lastly, if we take a look at our last subinterval from 2 to 3, my base is still a value of 1. Still a value of 1. But my height has to go all the way up to here. Here's my height. And my height of my function is my function value at the value of 3. Because that measures my distance all the way up to here. So that's why we want to make sure we intersect our graph so we can find the height of our function. So we have 1 times our function value at 3. 3 times 3 is 9 plus 1, so we have 1 times 10. So we have 10 squares. So to calculate our Riemann sum is 2 plus 2 plus 5 plus 10, which is 15 19 squares. This is our Riemann sum. This is our upper sum. This is our upper sum. Now, what you should be able to realize is you sit there saying, hey, Mr. Gregory, this is a little bit more because this area and this area and this area and this area is more than all this others, which is true. We are just approximating now. We are approximating because we're adding in additional areas here, which is okay because we're dealing with approximations. But what we could tell is if we're 19 squares, that's an overestimation. I'm not going to be higher than 19 squares. Another approximation, once again, that we'll deal with is called the lower sum. The lower sum is almost identical to the upper sum, so you'll be able to rewrite the exact same thing. So you can look at what you just wrote up above and you change one word. It's a Riemann sum of rectangles created by the partition lines, the x-axis, horizontal line intersecting the graph at one point and is entirely below the graph of the function. So we're going to be entirely below the graph of the function. So the upper sum is entirely above the graph of the function. Now we're going to go entirely below the graph of the function. So you can just recopy what you have up there. If you need to hit pause, that's fine, and recopy. And change this word to below. Where up here, we were above. It's going to be the same process as what we did before. We draw vertical lines at each partition line, extending above the graph, that's fine. Draw the horizontal line intersecting the graph only exactly one point, staying entirely below the graph, and then calculate the area of each rectangle. So it's going to look very similar to what we just did. My partition lines are still the same, -1, 0, 1, 2, and 3. My base here is still a value of 1. Let's take a look at -1 to 0. And let's look at the area from -1 to 0. Once again, our goal is we are trying to calculate this amount of area. That is our goal, to calculate this amount of area. So, to draw our top part of this rectangle, before we had to draw it so it's entirely above the graph of the function. Now we have to draw it so it's entirely below the graph of the function and intersecting our graph at exactly one point. So now my rectangle, my horizontal line is going to be entirely below the graph of my function. And I'm going to intersect my graph at exactly one point. What this gives me, once again, is this gives me a way of calculating the area of, the height of my rectangle. My base is still a value of 1. But now my function value that gives me my height is my function value at 0. That's my function value at 0. So I have 1 times 0 squared plus 1, so I have 1 times 1, which is 1 squared. And now this is going to look very similar to what we just did with the upper sum. But now we have to draw our horizontal line entirely below the graph of the function. So I'm going to draw from here. Stays entirely below the graph. So we have 1 times my function value at 0 again. So we have 1 times 1, which is 1 square. Now if we go from 0 or from 1 to 2, now we're going to draw our horizontal line. Okay, once again, we have to draw it so it's entirely below the graph of the function. So I'm just going to draw it there and I'm going to pull it down. So if I take a look at my bar, that was my upper sum. All we're going to do, whoopsie, is we're going to drag this line so it's entirely below the graph. If I drew it there, it's not entirely below the graph of the function, but if I draw it down here, pull it down there, now it's entirely below the graph of the function. But I still have this intersection point, this one intersection point, which is our function value at 1, that will give me my height. So we have area is equal to my base is still 1, but now my function value that I have at this point, that gives me my height of my rectangle, is the value of 1. So we have 1 times 1, let's see, it's 1 squared plus 1, that's 2, so we have 1 times 2, so we have 2 squares. And then lastly, my last subinterval from 2 to 3, my area, I still have my base of 1, but my function value that I want to have for my area, once again, has to stay entirely below the graph of my function, takes me to that point right there. And that horizontal line is entirely below the graph of my function, and this is a function value at 2. So we have our function value 2, so we have 1, let's see, 2 squared plus 1 is a value of 5, so we have 5 squares. Now to do my Riemann sum, we take our 1 plus our 1 plus our 2 plus our 5, so we have 7, 8, 9 squares. And that would be the lower sum. I mean, maybe sitting there saying, well, you know what, that's a little bit, let's see, I want the entire area, and this is a lot more less, or it's a lot less than what we had before. That's exactly right. But once again, we have an approximation. But what we can say is, let's take a look at the 9 squares and 19 squares. What we can say with this is the actual area is going to be somewhere between this 9 squares and this 19 squares. My area is going to be somewhere in between there. So we have 2 boundary values. 2 boundary values. And that's going to be a question for you. This is the upper sum and lower sum are 2 boundary values for the actual area. So these are going to be boundary values for the actual area. Well, what happens when we do a delta x of 0.5? Now what happens to my subintervals? Well, my subintervals now are going to be at -1, but now we're going to go at -1/2, at 0, 1/2, 1, 1.5, 2, 2.5, and 3. Oopsie. So my subintervals now, oopsie. start getting smaller. So now my subintervals are -1 to -1/2. -1/2 to 0. 0 to 1/2. 1/2 to 1. 1 to 1.5. 1.5 to 2. 2.5 to, 2 to 2.5. And then 2.5 to 3. We'll go through the upper sum here. What's going to be left for you for the homework is to do the lower sum for 1/2, and then you're going to do a 1/4. And you'll see something that will occur. And that's what the worksheet is that I posted for homework, is they're going to finish what we don't complete here. What has changed here is this distance for my base is now 1/2. But I still want to draw my rectangles so they're entirely above the graph of my function. Because we are dealing with an upper sum. And you'll see what you're going to have here is a lot of clicky-clacking. Oopsie. Don't want that. I don't know how to get this out. Oh boy. There we go. So what we have now is our area is 1/2 times my function value at 1. Then my next one is my area is going to be 1/2 times my function value at -1/2, because I'm using this value here. And then we have, for the next one, my area is going to be 1/2 times my function value at 1/2, because I'm using this value right here. So I'm looking at function values in specific points. Now once again, that's why we utilize the graph of our function, so we can find our height. So we have 1/2 times my function value at 1, which was 2. So we have 1/2 times 2. So this area is 1 square. Now if I use 0.5, if I square 0.5, I get 0.25 plus 1. So I have 1/2 times 1.25. And once again, I'm going to have 1/2 times 1.25. So I'm going to do this calculations for each one of these, for my upper sum, and then I'm going to have a lower sum. Once again, my goal is to get you started on this. What I want you to do is I want you to go ahead and complete what the notes are, and I've provided you some solutions to them also, so you can also refer back to the solutions to the worksheet that I've given. But your goal, once again, your graphs or your homework is this exact same thing, but you have a little bit more space, where I'm starting to run out of space here. But what I want you to do is go ahead and calculate your upper sum and lower sum for this function here, and see what happens to those two boundary values. We started out at 19 and 9 with my areas, my two boundary values. Let's see what happens when I start shrinking this delta x here. Okay, finish that for homework. We'll come back tomorrow. We'll go through a little bit of examples of that. We'll have some additional upper and lower sums. Just maintain the work that we're doing here. Get yourself a routine in regards to your schoolwork that you have here. Just maintain a routine here. Continue to keep your social distancing. I suggest that you continue to FaceTime people and talk to people. Give you some socialization that's going on there. But please do keep your social distancing so we can get back to some sort of normalcy here. But if you have any questions about this, feel free to comment to me. Outside of that, I'm out of here. Adios. Have a great day.